Hey guys, it's me, Andy, back at it again with ECE 524, and today we'll be doing a mixed language adder with both Verilog and VHDL. So let's go ahead and get started. Let's start off by opening up Vivado. And again, it takes a minute. Just have to be patient. I'm going up and opening up lab 2. Everything here is nice and organized. Keep everything within the same flow, you know. So let's go all the way down the hierarchy and start from the simple AND gate. So here you go. This was done in VHDL, and the XOR gate, the exclusive OR gate, was done in Verilog. So as you know, to make an half adder, it requires an AND gate and exclusive OR gate. And Vivado actually lets me use both languages to create a half adder. One was made in Verilog, one was made in VHDL. And here is my half adder, which is used in VHDL. And now to actually use the AND and exclusive OR gates in this module, we declare these gates using the keyword component. And a component is a reusable module that can be declared inside another module. Instead of designing a complex system, we can use these components to separate the design into smaller pieces, creating a hierarchy of components. And if we actually set this as top, we can see the schematic on how this actually works. Okay. Sorry, it takes a minute. So this is the hierarchy, and if you expand it, a half adder has two gates, the AND and the exclusive OR gate. It separates it into small components to make one big block. It's a form of abstraction, but it's really nice. Now, to make a full adder, we know that you need two half adders. And as you can see here, I didn't explain port mapping, but port mapping is the process of mapping the input and output ports of a component in the target module as shown here. And if I actually make the full adder top, as I'll show you right here, let's do this one. That's top. Reload. So we can see the full abstraction of the full adder. The full adder is made of two half adders, and each half adder has an exclusive OR gate. As you can see here, we can go ahead and expand that. This blows my mind that we can do this in HDL. But in Verilog, I was curious and I did it my own way. So in Verilog, which is right here, where is it? So in Verilog, I decided to wire everything directly. I wanted to see if I could make everything under one file, And if I actually run this and open the schematic, bear with me, Vivado is acting slow today. We get the same thing as the full adder with the hierarchy implementation. It's just that with the Verilog, everything is wired directly and under one file. But they both give the same result as we'll see later. So enough with that. Let's move on to the full adder, the chain full adder with multiple half adders, as you will, or the n-bit adder. Some people even call it the chain adder, but this type of adder is for large. It's for large binary numbers that can be constructed by cascading multiple full adders. The carry bit basically ripples from one stage or one adder to the next. This was done using the VHDL generic type, so that we can add as many full adders as we want when this module is instantiated. And if we set that as top, let's see how the schematic looks like. Let's go ahead and reload. And open up the schematic. So this is our full adder n-bit or ripple carry adder, and we have a generic of 4. So 4 is going to be our default value, but if you want, we could just keep adding as many as we want, which is the beauty of it. And now let's move on. This is my top module, which combines everything we've done, but it's in Verilog, much cleaner, as you can see. I typically I prefer Verilog. Have a sweet spot for it. And if I run the simulation, let's see how the hardware looks like. I'm sorry, this always takes forever, so again, just bear with me. This basically just adds a clock so everything is synced up together, because chaining adders might be difficult and run into issues. So it's better just to clock everything. And yeah, expand everything so you can see the full hierarchy. And there you go. And it's full glory. So in order to actually, to actually test our FPGA modules, we must create something called test benches. A test bench contains an instantiation of a design module, to basically build simulations of inputs and outputs to test the behavior of our code. We call it UUT, or unit under test, and it's a behavioral model of the environment around the RTL design. And again, RTL is register transfer level. I won't go into too much detail about that, but to start off with, let's look at our full adder, or actually half adder test bench. Let's do that one first. Set that as top. I'm sorry this takes so long. And run simulation. So as you can see, everything seems to be working. I like to put the clock at the top to make everything more organized. But yeah, everything is working. X plus Y. Get C a sum. Let's move this up here. There you go. That makes more sense. And if you wanted to see the code, there it is. Let's look at the full adder test bench. There you go. This is going to be the ripple carry adder test bench. But we can go ahead and test it if you'd like. Could run that real quick. Not a problem. Oh yeah, I forgot to close this. Vivado is so tricky sometimes. You gotta be careful. It could cause so much issues. And run simulation. Add your signals and run. Let's pause that for a quick second and just zoom in a little bit so it's easier to see. Yeah, and the full adder seems to be working. Let's just clean this up a little bit so it's easier for me to read. And yeah, that's a working full adder, all right. That's what I like to see. To save some time, I'll just show you the test bench code. Let's go back to sources and the n bits cascaded test bench. I'll show you the top module one. That's my top module test bench. Very easy to make. Just copy and paste your ports, make them components, instantiate. Very straightforward. And yeah, you know what? Let's test out the top module. Why not? This may be interesting, as you'll see. And let's run it. Okay, so let's go ahead and zoom in a little bit. Now this is interesting. So in the final design, let's move these to the top so it's a little bit more easier to read. So in the final design or top module, if we observe clock cycle 1 and 2, we get an output of 0 and invalid, which is the blue ones you see here. Also, the sum of x and y always shows up 1 clock cycle later. Now, I believe the reason why this is happening is due to something called propagation delay and timing issues. Since our code is all concurrent, it all runs at the same time. Each signal might have a future value, causing the results to be delayed by 1 or 2 clock cycles. But maybe in the future I'll figure some way to fix the bug or a problem. And it might not even be a problem. I'll have to look into it more. But that's pretty much it for this lab. Go back to our sources. But yeah, this pretty much concludes my lab 2, and this lab was extremely useful for me since, you know, my knowledge of VHDL is very minimal, and I come from a Verilog background, so comparing Verilog to VHDL was the best way to get myself familiarized with the language. switching back and forth really helped me learn the language, and the best way to learn is to get your hands dirty. I'm gonna leave you guys with that, and until next time, guys, peace out.